Hello students, I hope you are all well and studying consistently. Before starting the topic, I must say, whatever you do, do it with your confidence. And students, confidence, it's the key to achieve success. And confidence can be achieved only and only through your hard work. That's why I always keep on insisting, please believe in hard work. Do study on consistent basis. Okay, let's start with this particular topic, which is again very important one. We'll try to find out the expression for common potential and the loss in energy when two capacitors are joined together or are connected together, right? So, let us consider these are the two capacitors of capacitance C1 having charge Q1 and potential V1. And this is the first condenser, right? This is the first one. And let this be the second capacitor of capacitance C2 having charge Q2 and potential across the plates be V2. This is the second capacitor. Now what we intend to do in this particular article is that we need to prove that when these two capacitors are connected together, then the final energy of the system is found to be less than the initial energy of this system. So we'll discuss why there occurs a loss in energy, and then we certainly are going to find the expression for that loss in energy. And before that, we need to find out the expression for the common potential. Now look, in the previous class, class 1, you must have studied when a hot body and a cold body are brought in contact with each other. Then what happens is the flow of heat takes place from the body at higher temperature to the body at lower temperature. And this flow of heat continues till the thermal equilibrium is attained, till both the bodies attain a common temperature. So the same illustration is valid over here as well. When we connect these two capacitors through some connecting wires, what happens is charge sharing between the two capacitors takes place. That is, charge tends to flow from one capacitor to another capacitor. Obviously, total charge will remain conserved, but charge flow between the two capacitors takes place. And this flow of charge between these two capacitors will continue till both the capacitors attain a common potential. And that is what we are going to find, the expression for that common potential, right? So, let's start with the article. This is the initial scenario, right? What is the initial energy stored in this capacitor? It is half C1 V1 square. What is the initial energy stored in the second capacitor? It is half C2 V2 square. So, if we talk about the system comprising of these two individual capacitors, then what about the total energy of the system when they are not connected? That is the initial energy of the system. It will be obviously equal to U1 plus U2, and that will be given by half C1 V1 square plus half C2 V2 square. Put this as equation A. This is the initial energy of the system comprising of these two individual capacitors, right? Now what we do is, we connect these two capacitors through connecting wires, like this. It will be like this. These are the two capacitors when they are connected together. Capacitance, it's a constant term, it's a constant quantity, it depends upon the given capacitor, so it will remain constant, no change. So as I told you, when these two are connected together, what happens? Charge flow between these two capacitors will take place till both the capacitors attain a common potential. Let that common potential be V common. Let it be represented by this. So both will acquire a common potential. And after the charge sharing, after both the capacitors attain this common potential, let the charge here is Q1 dash and here let it be Q2 dash. Right? Charge sharing between the two capacitors will take place. Obviously, one capacitor will lose charge while the other will gain charge. But the total charge will remain constant. And as I told you, this charge sharing between the two capacitors will take place till both the capacitors attain the same common potential. Right? So let's first find out the expression for this common potential. For that, what we do is, I've always maintained, and you're also aware of it, we have discussed it with the property of charge. Charge is conserved. Charge can neither be created nor it can be destroyed. So what is the total charge of the system before they are connected together? It was Q1 plus Q2. What is the charge of the system after they are connected? It is Q1 dash plus Q2 dash. Right? Now we are aware of that basic formula, Q equals to CV. So what's the relationship between Q1, C1 and V1? Q1 is C1, V1. Similarly, Q2 is C2, V2. Q1 dash, it will be equal to C1, V common. Q2 dash, it will be C2, V common. So, take V common. In the bracket, it will be C1 plus C2. So, I am writing the result directly. So, what we get is, it will be C1, V1 plus C2, V2 divided by C1 plus C2. This is the expression for the common potential. There are certain numericals which are based on this formula. In such a case, you can directly make use of this formula, right? In case any of these two are uncharged, then C1, V1 or C2, V2, either of them would be 0, right? It depends on the situation. But this is the expression for the common potential. That is C1, V1 plus C2, V2 divided by C1 plus C2, right? So first part is over. Expression for the common potential is obtained. Now let's find out the loss in energy. So for loss in energy, we need to find out the final energy of the system, right? So let's find out the final energy of the system. Again, formula is half CV square, half, what is the net capacitance over here? Common potential, potential being constant, they must be connected in parallel. So what is the resultant capacitance of these two capacitors connected in parallel? It will be C1 plus C2. Formula is half CV square. So C net in the combination C1 plus C2. And what is V net? It is common potential. Right? So you can substitute the value over here. So what you get is half C1 plus C2 V common square. Substitute the value over here. C1 V1 plus C2 V2 divided by C1 plus C2 and whole square. So what you get is C1 V1 plus C2 V2 whole square divided by 2 C1 plus C2. Put this as C. So this is the initial energy of the system before they are connected together, and this is the final energy of the system after the two condensers or capacitors are connected together. Now, in order to prove that actually when they are connected together there is some loss in energy, we need to prove that U initial is greater than U final, right? For that we need to prove that U initial minus U final is greater than 0. So let's find out the loss in energy then. So, loss in energy, it can be represented by del U. It will be equal to loss means initial energy of the system minus final energy of the system. Now, simple mathematical statements are involved. We are aware of U initial, we are aware of U final. Simply substitute these values and you should get the result. Let's do it. So, what we get is del U. So it is, let me write this step, half C1 V1 square plus half C2 V2 square plus C1 V1 plus C2 V2 whole square divided by C1 plus C2, and it is twice, right? And with negative sign obviously. We are subtracting loss in energy, means we are subtracting these two. So it can be easily evaluated. Let's do the mathematical part. Let's try to get the answer, right? So, del U. LCM can be taken. LCM is twice C1 plus C2, isn't it? Twice C1 plus C2. So C1 V1 square, it will get multiplied by C1 plus C2 plus C2 V2 square, it will get again multiplied by C1 plus C2 minus C1 V1 plus C2 V2 whole square, isn't it? It can be expanded. It's in the form of A plus B whole square. So what we get is del U is equal to, let's open the bracket. So we get C1 square V1 square plus C1 C2 V1 square. Similarly, open the bracket over here. We get C1 C2 V2 square plus C2 square V2 square minus, it's in the form of A plus B whole square. So I'm opening the bracket as well. C1 square V1 square minus C2 square V2 square minus twice C1 C2 V1 V2 divided by twice C1 plus C2. Right? This is the expression which we will obtain. Still further, it will get cancelled. C2 V2 square, this one will also get cancelled. So we'll be left with C1 C2, I think it can be taken as common. We'll be left with V1 square. Here we'll be left with V2 square. Over here we'll be left with minus twice V1 V2. Okay, last term. So half C1 C2 divided by C1 plus C2, it can be written in this manner, V1 minus V2 whole square. This is the expression for the loss in energy when the two capacitors are connected together. Now observe this particular formula. Now capacitance of a capacitor, that can't be negative, right? V1 minus V2, even if V2 is greater than V1, still it's a term which involves whole square. So V1 minus V2 whole square would be always positive. So what we have proved is del U is greater than 0. That is U initial minus U final, it is greater than 0. Which further implies that U initial is greater than U final. Means when the two capacitors are connected together, then the final energy of the system is less by this amount than the initial energy of the system, comprising of the same two capacitors. So students, it has been mathematically verified that there does loss in energy takes place when the two capacitors are connected together. And the loss in energy is given by this particular expression. Half C1 C2 divided by C1 plus C2 and multiplied by V1 minus V2 whole square. So that's the formula. You can make use of this formula directly while solving numericals based on this topic. Right? One more thing. Students, can you predict where this energy loss takes place? Why this energy loss is taking place? Yes, it is because when the two condensers are connected with the connecting wire, we are not using superconductors, they are connecting wire, offering some sort of resistance, right? So in order to overcome that, some energy gets consumed in that, and that may appear in the form of heat. So this loss in energy appears in the form of heat because of the resistance offered by the connecting wires. So that accounts for the loss in energy during this process. So this marks the conclusion of this particular topic, right? Okay students, before proceeding with some other theoretical topic, let's discuss some basic numericals based on the topics which have already been taught to you, which we have already discussed. So let's discuss some simple conceptual questions, right? So first question is a graphical one. Two capacitors having capacitances C1 and C2 are given. Once they are connected in series, and then maybe they are connected in parallel. QV graph is plotted between them. graph is plotted between them. So the graph obtained is like this. This is suppose A and this is B. Look, again I am repeating the quotient. Two capacitors of capacitances C1 and C2 are given. They are connected in series and then the same two capacitors are connected in parallel. And QV graph is plotted in both the cases. Which one of these two, A or B, represent series grouping of the two capacitors and the parallel grouping of these two capacitors? That you need to tell, right? So how to approach this question? First and foremost, we are aware of this formula. Q is directly proportional to V, or Q is equal to CV. This is constant, this is capacitance. So it's in the form of, if Q is represented along y-axis, V, potential difference, is represented along x-axis, then it's in the form of y equals to mx. Students, it's the standard equation of a straight line passing through the origin. So first point to be noted is that the graph between Q and V being linearly dependent with each other, it would be a straight line passing through the origin. And what about the slope? M is the slope, right? So the slope of this graph will give us capacitance. The slope of this graph will give us capacitance. Okay. Slope, as you are aware, it's equal to tan theta. This is suppose theta B and this is suppose theta A. Obviously, theta A is greater than theta B. Therefore, tan theta A is greater than tan theta B. Obviously, it is much steeper, right? Therefore, slope of A is greater. That is, slope of A is greater than slope of B. Therefore, CA is greater than CB. Net capacitance in case A is greater than the net capacitance in case B. This we can safely conclude. Now what happens is, you need to understand or you need to recall the concept that whenever the series grouping takes place, the net capacitance decreases. There we apply the formula, which is 1 by C equals to 1 by C1 plus 1 by C2. So the resultant capacitance in the series grouping of capacitor decreases. While if the capacitors are connected in parallel, then the resultant capacitance increases, as the formula is C equals to C1 plus C2. So the net capacitance is greater in A case. So A must represent parallel grouping, while B must represent series grouping of capacitors. Because in parallel, the net capacitance increases. In series, the net capacitance decreases. Right? Actually, the same question can be modified as well. Suppose the same question. This is V and this is Q. And the same question. This is A and this is B. Same question. What I have done is Q and V are interchanged. Right? Same question. That is two capacitors of capacitance C1 and C2 are given. Once they are connected in series and then they are connected in parallel. Which of these two A and B represent series and parallel grouping? Right? So in this case, slope will give us V by Q. In this case, slope will give us reciprocal of capacitance. Remember that. So you need to identify the coordinates and the physical quantity which is represented by those coordinates. Right? So in this case, the slope of the graph will give us reciprocal of the capacitance. Slope is y2 minus y1 divided by x2 minus x1. So over here V by Q, that is 1 by C. So in this case, slope obviously of A is greater than slope of B. A slope is much steeper. Therefore, 1 by CA is greater than 1 by CB. Therefore, CB is greater than CA. So here the resultant capacitance in case B is greater. So B must represent parallel grouping and A must represent series grouping. So students, do ensure to check which physical quantity is represented along the y coordinate and along the x coordinate, and accordingly proceed with the solution, right? Logically. Let's discuss some other question as well, right? So, next question is, it's based on some numerical values. Suppose two capacitors C1 and C2 are given. When they are connected in series, their resultant is, suppose when they are connected in series, their resultant is 2 microfarad. When they are connected in series. And the same two capacitors C1 and C2, when connected in parallel, suppose their resultant is 9 microfarad. What are the values of the capacitances of the individual capacitors? What are the values of C1 and C2? Let's do it. Now look, in parallel, what's the formula for parallel? C1 plus C2. It's given to be 9. I'm going to state C1, C2 in microfarad. So put this as equation 1. In series, what's the formula? C1, C2 divided by C1 plus C2. It's 2. C1 plus C2 is 9. Therefore, C1, C2, it becomes 18. So these are the two equations. Now we have got two variables C1, C2 and two equations. Now it can be solved in various methods, right? One of the method is, you can write this, C1 minus C2 whole square. It may be written as C1 plus C2 whole square minus 4 C1 C2. This is another form. A minus B whole square is equal to A plus B whole square minus 4AB, right? So, what do you get is C1 plus C2, it's 9 square, we get 81 minus 4, C1 C2, it's 18. So it is 81 minus 18, 4, that is 72. It is 9. Therefore, C1 minus C2 is equal to 3. Right? Plus minus 3 actually, but capacitors can't be negative, so I am considering only the positive sign. Now consider these three equations, add them and you will get the value of C1 and C2. So very simple. So adding these two, what do you get? C1 plus C2 is equal to 9 and C1 minus C2 is equal to 3. So add these two. Twice C1 is equal to 12. So C1 is equal to 6 and I have taken it in microfarad. This is the first answer. And if C1 is 6, then C2 would be equal to 3. So it's very, very simple. So that's the correct way of doing such questions. It won't take much time. You can also cross check it. When they are connected in parallel, then the formula is C1 plus C2. So 6 plus 3 it will become 9. When they are connected in series, then the formula is 6 into 3 divided by 6 plus 3. That is 18 by 9, which will give us 2 microfarad. So students, do practice more and more numericals, right? Well, the next theoretical portion will start in the next session.